Okay, today 2.4 Algebraic Reasoning. Really this section is get you ready for proofs. So the first thing I'm going to do is cover some of the properties you've used in the past. So for instance, subtraction property of equality just says if A equals B, then A minus C would equal B minus C. Really just means you're subtracting the same thing from both sides of an equation. So for instance, if I had 4 plus x equals 7, I would just subtract 4 on both sides. When I subtract 4, I'm using the subtraction property of equality. It gives me x equals 3 there. Okay, that's an example of the subtraction property of equality. Let's try another one. For addition property equality, it just says if A equals B, then A plus C equals B plus C. So, rather than subtracting the same thing from both sides, maybe now, not maybe, this time, you're adding the same things to both sides. So, for instance, if I had negative 4 plus x, I'd have to add 4 to both sides to solve that equation. If you think back to your algebra days, the good old days of algebra, get x equals 11. All right, so you're adding the same thing to both sides. The next one would be multiplication property of equality. So if A equals B, then 4 times A, not 4 times A, excuse me. Thinking ahead to my problem there. Then A times C equals B times C. And so let's say I am stuck with a 4 here. Okay, you know what? I'm going to go ahead and use it there. A divided by 4 equals 16. All right, to solve that, I have to multiply both sides by 4. Okay, there and there. That is the multiplication property of equality. There. Hopefully that 4 is out of my system now. Okay. Division property of equality. So most of you probably can guess it. It means you're dividing the same thing on both sides. But if A equals B, then you'd have A divided by C equals B divided by C. And so once again, let's say, you know what I'm going to use my buddy for. 4 times A equals 24. So in this case, to solve this, I have to divide both sides by the same thing. That's using the division property of equality. So get A equals 6. All right. Now substitution. Substitution property of equality says this. Well, let's say I have, actually let's put it out in words first. Substitution property of equality says if A equals B, then A can be substituted for B in an equation or expression for that matter, okay? But we're going to use it in an equation. So for instance, A equals B, so 4A equals 24. We solve, we get 6. So what we could do is to check our work, just like you've done in the past, you substitute 6 in for A. Okay, so you substitute this back in for A, you solve, you get, well, hey, 24 equals 24. It's true. It works out. Distributive property. Many of you recognize that term. So that just says, I'm going to just give an example. 4 times x plus 5 equals 4x plus 20. Kind of in letters, I guess the way you could write it out if you're putting it in a general term, you're saying A times B plus C equals AB plus AC. And you could use subtraction in between. It could be minus in here, and that would do the same thing. All right, so some quick review there. Let's try some others. Associated property of addition and multiplication. So I'm just going to use the letter form here real quick. So I'd have, say, A plus B plus C. And that's equal to A plus B plus C. Associate means we have different groups. So if we group A plus B and then add C, that's going to be the same as if you group B plus C and then add A. So for instance, I'm going to work my way up here on this one. Let's say I have 4 plus 5 plus 6. So A is 4, B is 5, C is 6. And so we'd have 4, 5, and 6. And all that really means is 4 plus 5, which is 9. 9 plus 6 is going to be equal to 4 plus 11. Okay? Well, 9 plus 6 is 15, and 4 plus 11 is 15. So it works. Okay? If we used it with multiplication, all that really says, let's switch up the colors here. All that really says is A times B times C equals A times B times C. But it just says you can multiply those different groupings in a different order there. So let's use 4, 5, and 6 again. 4 times 5 times 6 is equal to 4 times 5 times 6. So going parentheses first, that would say 20 times 6 is equal to 4 times 30. And we know that both of those equal to 120. Therefore, hey, it works out. That is the associative property of addition and multiplication right there. All right. The commutative property of addition. Commutative property of addition and multiplication says this. Let's deal with addition first. It says A plus B equals to B plus A is equal to B plus A. Commute means to move, so really it just says, hey, you can change the order you add and it's not going to change the answer. So for instance, if I had 4 plus 5, that's equal to 5 plus 4. If A is 4 and B is 5, it gives you 9 equals 9. And that works for multiplication as well. So we'd have A times B equals B times A. Or 4 times 5 equals 5 times 4. 20 equals 20. Most of us are like, yeah, we already know that, but hey, they're properties you've used for a long time. Now you'll notice on both of those there's not an associative property of subtraction or division, nor is there a commutative property of subtraction or division. So for instance, in commutative, A minus B, so 4 minus 5 is not equal to 5 minus 4. 4 minus 5 is negative 1, 5 minus 4 is 1. A divided by B would be 4/5, B divided by A would be 5/4. It doesn't work for division. You'd find the same thing up here with multiplication and addition when you're dealing with associative property. It doesn't work for subtraction and division. Okay, identity property. Well, identity property for addition. Identity says if I have A, what could I add to A and still get A? Well, the answer is 0. That's the identity property of addition. Multiplication property, or identity property of multiplication says, what can I multiply by A and still get A? Well, hopefully you know that would be 1, usually shown as 1 times A equals A. Anytime you multiply by 1, that is the identity property of multiplication. And then the last one is the zero product property. And zero product property just says, hey, anytime I multiply something by 0, I get 0. You used that a lot when you did algebra last year. All right. 3 other properties, the reflexive property, intransitive, and symmetric. All right, so first the reflexive. And by the way, I'm going to actually show these using real numbers. Then I'm going to show them using, say, segment lengths. And then angles. And the reason I'm going to do that is because that's how you're going to be using them when you deal with geometry later, well, even a little today. So when you're writing proofs. So if I look at it in terms of real numbers, it's not a very like aha moment here for reflexive property. It just says reflexive A equals A. A equals A. It's not reflective, it's reflexive. I know that seems weird, but A equals A. In terms of segments, we could say like A, B. You know what, let's use capital letters on this. Okay. AB equals AB. So if you're dealing with segment lengths there. And then say angle measures, we could say the measure of angle A equals the measure of angle A. Okay. So segment lengths, angle measures, I guess I'll add the word length here. That is really what you're dealing a lot of times when you're dealing with reflexive property. The transitive property and the symmetric property. Transitive property is a little more intense. Transitive property says, and let me switch colors here. Let's go with there. So transitive property says if A equals B and B equals C, then A equals C. And some of you will look at that and go, whoa, that's like the law of syllogism. And it really is. I mean, these two pieces are the same, therefore A equals C. All right? So in terms of segment lengths, really what that means, if we kind of stick with the AB, we could say, you know, I better use if. If AB equals, say, BC, oops, I can't equal BC. How about CD? Such a rookie mistake. Unbelievable. Okay, CD. And CD equals EF. Then AB equals EF. Notice these two pieces are the same. Therefore, it's like we almost just throw them out. We put AB equals EF. Not, you know what? Whoa. You know what? I put an extra line there. There we go. So AB equals EF. And then in terms of angles, we'd say if the measure of angle A equals the measure of angle B and the measure of angle B equals the measure of angle C, then the measure of angle A will equal the measure of angle C. All right, that's the transitive property. Okay, so when we have these pieces that are the same, there and there, here and here, and here and here, it's like we throw those out and we keep the front and the back. Symmetric property, another one that's not like a big wow, but it's, you know, it's one that we use. It says, symmetric says if A equals B, then B equals A. And some might go, well, that's just like the commutative property, and it is just kind of like the commutative property. Okay. In terms of segments, that would say if AB equals CD, then CD equals AB. And in terms of angles, if measure of angle A equals measure of angle B, then measure of angle B equals measure of angle A. All right. Well, let's go ahead and move on here. Next thing we're going to do is just solve an equation and justify the steps, kind of telling what we're doing each step here. All right. So the first step, I'm looking at simplifying the left-hand side. So I'm going to distribute that -3. So 75 minus 6x, that's a 6, And negative 3 times 5, negative 15, equals 24x. And listing out my work here, that is, or my steps, distributive property. And you can add of equality, but I just put distributive property. Okay? Oh, kind of showing you a little of the future there. Make sure I spell it right. All right, and then from there, I'm going to look at 75 minus 15. Well, 75 minus 15, that's like terms. That's 60. 60 minus 6x equals 24x. Really what I've done there? Combine like terms. All right. Now, since I can't simplify either side, I'm going to start moving things, or moving my variables to the same side. So I'm going to add 6x to both sides. Okay. So let's get rid of that little subtraction sign I put. But we add 6x to both sides. Here we get 0, and here we get 30x. That's equal to 60. Now, some classes will, it's okay if you just write, well, really all you've done here is done the addition property of equality. And if you write that addition property of equality, okay, don't write that out yet because I'm going to show you another piece. If some teachers are fine with that, some teachers will actually want you to put two different steps there. They want you to take that piece you just wrote there, and in fact, some computer programs, and they're going to say, hey, show that that is the addition property of equality right there. And really, after you applied the addition property of equality, then you combined like terms to get to here. So from this line to this line, addition property of equality, oops, and then from this line to this line, combine like terms. I'd probably be fine if you just used the addition property of equality and skip the combine like terms and just put the addition property of equality down here. But I want to make sure I show both pieces there. Last thing, I'm going to divide both sides by 30. Okay, that leaves me with 1x equals 2. And once again, same thing, division property of equality, and then simplify. Some are going to be fine if you just write division property of equality, put this piece right down here, and skip the word skip the simplify. Just say that's what you did there. I would probably be in that boat, but I know that some teachers wouldn't, and some computer programs where you have to enter the answers online won't. They'll have that extra step, so I want to show that. Okay, well now let's try to deal with an actual picture. Okay, and so we have this picture, and what we need to do is show that y measure of EBC, so E to B to, excuse me, E to C to B, ECB, is congruent to DCA. And so the first thing we could do is we could see that angle 1 is congruent to angle 3. So I'm going to actually write that and say, well, measure of angle 1 is equal to measure of angle 3, and they're equal because they're given. That's given by the markings. Okay, and so really I'm kind of getting into a proof here. They're marked into the diagram. Okay. The next thing I could do, I could say, well, I can see that, like, if I'm planning this, I'm looking through it, well, I'm like, man, if this is the same as that, and they both have the same, they share the same angle, then obviously they have to be congruent to each other. Well, you have to be able to state that. So really, I'm going to start by saying, well, I know that EC to B is made up of these two things. And then I'm going to say that this is made up of these two things. Okay? And I might have a step or two along the way, but I'm going to at least say that. So E to C to B is made up of 2 and 3. The reason I'm saying that is because that's what I recognize to begin with. I said, well, this is made up of those two. This one's made up of those two. And these two are congruent. Therefore, since they share the same angle, don't they have to be congruent? And yeah, they do, but you have to be able to prove that. So the first step is to say what you're thinking. So ECB is equal to the measure of angle 2 plus the measure of angle 3. And how do I know that? That is called the angle addition postulate. And that's one you learned earlier this year. It's where these two angles, the two smaller, make up the bigger. Okay, and maybe even better yet, rather than using that marking there, the two smaller make up this bigger angle. Okay. Now, I could also go in, and after I've said that, I start looking around like, well, hold on. If angle 1 equals angle 3, and that's an angle 3 there, I could actually say angle 1 here. I'm kind of getting ahead of myself, so I'm going to leave myself a little room, and I'm going to go measure of angle, and I'm going to say that this angle right here, DCA, is made up of 1 and 2. Measure of angle DCA is equal to the measure of angle 1 plus the measure of angle 2. Once again, angle addition postulate. Notice I started abbreviating there. Okay, now I have that, so I've now, if I kind of use my highlighter and use a different color, I can say, well, look, I've said now that. Okay. Well, now, what I can also do is I can look at this and go, look, angle 1 is the same thing as angle 3. Like, wherever I see an angle 3, I can put an angle 1. All right? And so what I'm going to do is I'm actually going to do that. I'm going to say right here, I'm going to say, well, I could also say measure of angle ECB. It's not just measure of angle 2 plus 3. It's also measure of angle 2 plus measure of angle 1. And how do I know that? I use substitution. Use the substitution property of equality. All right. Now, please note you have this and this. Okay? I could switch those around and use commutative property, or I could just rewrite the second one. So, I'm going to rewrite that second one and just, because I could have wrote it in any order just to make it a little more clear. There's 2 and there's 1. So DCA is made up of angle 2 and angle 1. That's still true. And notice they're the same thing now. ECB equals angle 2 plus angle 1. DCA equals angle 2 plus angle 1. Therefore, the measure of angle ECB is congruent to the measure of angle DCA. And how come? Well, I know that's true because of the transitive property. And remember the transitive property? Transitive property says, hey, if this is equal to that, and this is equal to that, then these two have to be equal to each other. That's kind of what we did. Remember? Right here. All right. Whoops. Very good. By the way, when we're dealing with proofs, this is like a 2-column proof here. Kind of broke out of my column on this last one. There we go. These would be called statements. These over here would be called reasons. All right. And I kind of skipped one here at the end where I actually should say that this equals that. And then congruent angles are all angles that are equal are congruent. But I didn't go there. Based on what we have, I think we're good. Okay. Or if I changed it and just got rid of the congruent and put equal, that's probably what I should have. This should probably read that equals that. Probably just a typo by me. Okay, we're going to do one more. Dealing with properties of equality and dealing with, you know what, that's not angle measures. This is more segment measures. So the first thing you could do is just fix that on your, if you're taking notes, let's get rid of that. Let's call that segment measure. When I type this up, I probably just cut and paste the title, but previous title there. Of course I did. All right. So a couple typos, but show that the distance between AD and is the same as the distance between BC. All right. So first step, if I'm gonna try to just do it as a proof. Statements and reasons. All right. 2-column proof. And usually you number them, not like I did in my last one. So my first is going to say, I look at it and I look at, well, AC is congruent to DB, and I know they're equal, and I know that because it's given. I know that AC equals DB, and that's given. And I'm going to actually number these. Reason 1 goes with statement 1. All right? And I'm going to kind of do a similar approach, because when I look at this and I want to say, well, the distance between AD and BC are the same because, well, look, this little piece and this little piece are the same, and then they share a common piece, kind of like we did in the previous problem. So I'm gonna once again talk about, well, this distance is made up, the distance from B to C is made up of C to D and D to B. Okay? And so what I'm going to say is, I'm going to say, well, for my second statement, I'm going to say that BC equals CD plus DB. And that is called the segment addition postulate. All right. And then I can kind of go the same route. I could say, like for statement 3, I could go, well, I know that from A to D, that's made up of these two. So I could say AD equals, and well, I could say, whoa, I don't want to do that. I could say CD plus AC. And once again, segment addition postulate. Now, a lot of times in proofs, you would maybe put this and this separated by a comma and use one. You'd only have to write that out once, and I'll show that later. But number 4. So really, what I'm doing on number 4, well, if you kind of evaluate this, man, it'd be really nice to be able to somehow kind of do what we did on the previous one. You could kind of go on this one rather than looking at it like that. Is you could look at, notice you have DB here and you have a DB there, and notice you have AC here and you have an AC here. Well, you're adding CD to both of those. So if I were to take my original statement, and let's go back to black here. If I was to take my original statement AC and leave a little room and DB, and I were to add CD to both of those, notice I'm adding the same amount to both sides. So when I do that, I'm really doing the addition property of equality. And note, by doing that, what I've said now is AC plus CD is equal to DB plus CD. Well, note what that means. That means if I look down at statement number 5, since AC plus CD, notice AC plus CD up here, another name for that is AD, equals DB plus CD. Well, notice DB plus CD, another name for that is BC. Since we have those two things, we know that AD equals BC. And that is what we've done there, is we've used substitution. or the substitution property of equality. And we have now proven that the distance between AD and BC are the same. AD equals BC. All right. Very good. Or we've shown it. I guess there might be another statement to actually put that into a formal proof, but that's pretty darn good. AD equals BC, and we've used our properties of equality. All right. Well, good lucky.